To discuss is just some detail of what I did before. So first I'm going to discuss something that I had some question. How you project on the ground state, the ground state through path integral. That's an easy application of what we did last time. Then I want to discuss a bit about the stationary, well, the emergence, let's say, of the semi-classical limit. And then I'm going to discuss shortly how you define the impulsion operator. And in connection with that, what is the nature of quantum trajectories? Well, it's not proper in the path integral. You'll see already some interesting stuff going on. And then I think I'll stop there. And then I'll start to discuss path integral for the quantum field theory in the case of the free, or the Klein-Gordon field, so the scalar free field. Okay. So let's go back to what we did yesterday. I discussed how you can define both path integral in real time and path integral in imaginary time. So that's a mathematical construction which allows to construct, for instance, expectation value of operators in a Gibbs state. So we have seen that if we consider the Gibbs states at temperature T. So always for my system of a particle in the potential with Hamiltonian like this one, then we have the density matrix is just 1 over z beta exponential of minus beta h, where z beta is a trace of this operator. This is a density matrix. And we have seen that we can define what is the expectation value of, for instance, some operator A in the Gibbs state beta, which, well, by the formalism of quantum mechanics is just a trace of rho beta times the operator A. In a path integral formalism, so this number can be represented as a path integral is 1 over z beta times the path integral over Euclidean trajectories, which are periodic trajectories. Periodic in Euclidean time, with a period tau, which is h bar over beta. So h bar divided by the temperature. And the phase is exponential minus 1 over h bar, the Euclidean action for this quantum trajectory. And in addition, you insert the operator A expressed as a function of the position Q at a given time. So you have our periodic time. You have periodic trajectory in Euclidean time from 0 to tau, or tau beta if you want to be sure. And the Euclidean action, we wrote it, we expressed the Euclidean action for a given trajectory is the integral over Euclidean time of m over 2 q dot of sigma squared plus v of q of sigma. So the difference with the action at real time, the action of classical mechanics, is that there is a plus instead of a minus. Okay. Good. And z beta is, of course, represented by the same path integral without the a. So this is a ratio of two path integral. Okay. So now, of course, well, both in particle physics, in quantum mechanics, but especially in quantum field theory that we are going to discuss, one is interested into, yes?
In going from QFT to statistical mechanics, you replace Q of S by Q of sigma, I assume.
Yeah, no, sigma is just, I write the time variable sigma when it's Euclidean, and S when it's time just to remember. Like, it's just a notation.
Like in one notation, there are two different functions, right? Like Q of 1 and Q of 1 in the other, they're not the same thing.
Right. There are different functions. You integrate over a space of function. So you have no... you have a space of function. I'm going to describe this space of function. The space of function is, in fact, slightly different. But you integrate over the space of all functions that goes from... You see, you integrate for the space of function that to a given sigma associate a Q of sigma, or to a given real-time associate of QS. So this is what I call an history in Euclidean time, and this is what I call an history in... But you don't need to name any bijection because you just have here you have a space of function. So let's say, I don't know, you see, you have a space of function, and here you have a space of function. But you don't need to have a bijection.
There doesn't need to be a connection, but you did use a connection to derive.
No, there is a connection between the integral. I can relate. I can express quantities, correlation function relative to real time in terms of some integral of a space of function, and expectation value at Euclidean time, well, expectation value on over Gibbs state as another integral over the same space of function or similar space of function. The important is the integral and the space of function, but you don't need to make a bijection between the points.
But you did. When you derived the Euclidean action, you wrote down a derivation from.
But my derivation was a dictionary.
Was what?
Yeah, my derivation was a dictionary, but I didn't really use.
You actually used an equality there.
Yeah, but the equality was okay. So you can think about what I did by indeed using a bijection, but in fact it was a shortcut for doing the calculation precisely by if you repeat the derivation of the construction of the path integral by cutting the time interval into small pieces and computing small propagator, you just have formula similar for the propagator at Euclidean time and the propagator at real time at short time. And in that case, you don't really need a dictionary. Need a bijection.
You can do it properly.
Yes. I said, okay, let's do as if there was a bijection and you get the result, and I told you this is the correct result. But you don't really, I think it's a bad idea to think about the fact that there is a bijection. But you can do that at a mathematical level. Okay, so let me go. So what? Yes, so I was going back to the fact that, especially in quantum field theory, you have seen in QFT1 that an object important are the Green's function. I don't know how do you call them, or the Whiteman functions. So they are expectation value of products of operator constructed out of the creation and annihilation mode operator acting on the Fock space of the field, but taken between the vacuum, the ground state, the unique ground state of quantum field theory. So the question is, for instance, for this simple A, how do we compute the matrix element of this? Where this is a ground state, Okay? Well, it's quite easy because simply remember that A beta is just trace of rho A. So this is an exponential So if we have an Hamiltonian H with eigenstates, energy eigenstates, let me call them E, with energy eigenvalue EI, this is energy level. And so 0 is the ground state, and we have E0, which is the energy of the ground state, which is less than E1, less than E2, etc. Then we know that rho beta is just, it's just the sum, 1 over z beta times the sum over energy level of the projection operator times E minus beta EI. So this is a Boltzmann factor associated to the energy level. Okay. And so you see that, and z beta, of course, is just sum over I of E minus beta EI, which is finite since this goes to infinity and beta is positive. Okay. So you see that if you want to project, what you simply have is to take the limit when the temperature goes to 0, namely when beta goes to infinity. And you get O, A, O. Because the dominant term in this sum, when beta becomes large, is the first one. And the dominant term in the denominator is also the first one, and they cancel. So I'm just stating the fact that rho at beta equal infinity is just the projection operator on the ground states, because the density matrix then becomes a pure state. Okay, good. So now in the path integral formalism, this corresponds simply to let beta goes to infinity, you see? So projecting on the ground state, beta goes to infinity is equivalent in the path integral to take the period tau beta goes to infinity. Because remember, we have this fundamental relation. The period is h bar times beta. So t goes to 0, beta goes to infinity, period goes to infinity. So this means that at finite temperature, you have a periodic Euclidean time, and at 0 temperature, you may consider that Euclidean time is infinite. Well, with proper boundary condition at infinity, so that in fact it's a limit of periodic time when it becomes infinite. So this means infinite, if you want, Euclidean time. Let's say, line. Okay. And that's going to be something very, very general. Okay, so projecting onto the ground state is equivalent to take an infinite line for Euclidean time instead of a periodic time. Okay. Good. Okay. So now let me discuss what's called the semi-classical limit. I think I discussed that very shortly. There was a question on the first day. So let me go back either to real time, physical time, t. Then we have seen that if you want to compute a propagator, simply for instance the amplitude that when you start from some initial condition at time 0 or at time t initial, you end up at t final. We have seen that this is a path integral with q of ti equal qi and q of tf equal qf of exponential of minus, I over h bar s of q. Okay? And similar for the Euclidean propagator for at imaginary time, Ke of Qf tau f Qe tau I is the same thing, exponential -1 over h bar Se of Q. I'm writing once more, once again, this formula. Okay. So the question is, by semi-classical limit, I'm meaning something simple. I'm simply considering that I'm considering a given dynamical system, classical system, given by a given Hamiltonian, and I want, when I quantize it, I introduce commutation relation between the Q's and the P, and the commutation relation involves the h bar. And I want to understand what's the behavior of the system when I take h bar. I consider it as a parameter. What's happening when h bar is very small? So when the dynamics becomes classical, when the commutator of the quantum operators becomes the Poisson brackets of the classical corresponding quantity. Okay, what it means. When commutators, for instance, QP becomes Poisson bracket, but by some proper redefinition. Okay. Well, this kind of integral, we integrate over something, an exponential of I over h bar times some function of Q. There is a mathematical theory to understand how this behavior, this kind of integral behaves, which is called the saddle point approximation.
How exactly can you take a limit from a commutator and end up with Poisson brackets?
Well, if you work out properly in path integral, what is the relation? You can define a classical object out of the quantum object and check in the algebra that the Poisson bracket for quantum operator, they become that. I think I don't have time to do that, but this is, for instance, there is a whole theory of that which is called quantization by deformation. I'm not very explicit. I'm sorry. I think it would take too much time, but let me. Brackets. How can I define? Well, I have to think a bit if I want to find a very straightforward definition. But you might, perhaps in the quantum mechanics course, you have been, I think, introduced to the Bloch sphere for spin and to Wigner states. No, Wigner function, Wigner quasi-probability distribution. Okay. And so there are functions on phase space, but functions that are not like probabilities on a phase space for a classical system, but some quasi-probabilities on a quantum phase space. Okay. And if you realize how the quantum operators are realized as some sense linear operation acting on the Wigner quasi-probabilities, in the limit, in the semi-classical limit, where sometimes h bar goes to 0, those operators becomes Poisson bracket on function on the classical phase space. Okay, I can show you that, but it would take some time. It's not, you cannot do that in 2 lines of calculation. Anyway, on h bar. Okay. In fact, if you can say, you see, you have QP in quantum theory, QP equals I h bar. And if you, so of course you would say when h bar goes to 0, this goes to 0. But if you can realize Q and P as operators acting on quasi-probabilities, I think that you have an operation. So this becomes some kind of operator. This is P, and the commutator becomes, there is some kind of product that's correspond to the products of operator, but acting on function on quasi-probability. So the propagator is something like that. The commutator is P star Q. So you have something, you have some star operation, which is a deformation of ordinary multiplication. And when you take the semi-classical limit for this object, then you get, of course, 0 at leading order. But then you get, well, you get I h bar, which means that if you have some function, in some sense, that's what it is. If you have some function of Q and P, you get the, so instead of that, if you take the Poisson bracket, if you take the Poisson bracket for two functions, F and G and F, what you get is 0 at leading order plus I h bar times the Poisson bracket of the function F and G, sorry. Okay. Okay, but I prefer to stop there. There is a well-defined way to see this analogy, but let me stop. It would require half a lecture to do it. Okay, sorry if you are not satisfied. You are entitled not to be satisfied, but there is a clear answer. Okay, so let me go back to this. So let me first consider the, if you want, the propagator at imaginary time, because it's simpler, because then you sum over trajectories with a weight which is exponential of -1 over h bar SE of Q. And of course, this is a positive term. The action which was written there is the sum of one bounded term and kinetic energy, which is positive. So you see that the biggest term here is a term where SE of Q is smallest. You see. So, in fact, for this imaginary time, when h bar goes to 0, the dominant contribution is the minimum of SE of Q. Okay. And in this approximation, this is going to be, in the first leader, given by exponential of -1 over h bar SE of this Q minimal. Okay? And then there is going to be some coefficient in front, some normalization factor, which is related to the second derivative of SE of Q, and then some subleading contribution. So, when h bar goes to 0, only one trajectory dominates. Or several, if you have several trajectories that contribute by the same factor, but that's not the generic case. It's an interesting case, but it's not the generic case. And so this solution, this Q minimal, is called the saddle point of the action. Q minimal. So remember, it's a trajectory. So it's a given trajectory as a function of sigma. This is Q minimal of sigma. It's a given trajectory. This is called the saddle point of the integral. And it's called the saddle point because if you think about the fact when you have just an integral of the form integral from -infinity to +infinity of dq e exponential -1/2 some number a times q squared, or q minus q naught q squared. Consider a Gaussian integral. Okay, so that's one very simple case. You have no time. Then you can compute this. And let's assume that you have a 1 over h bar here, the parameters. You assume that a is very large, or that h bar is very small. well, you can perform the Gaussian integration. What you get is square root of 2 pi h bar divided by a, exponential of minus 1 over 2 h bar. And that's, you get just this number. Well, you have no h bar, so I would say this is a function, this is a parabola, so it's a Gaussian integral, which has a minimum at q naught, and the minimum is b. And a is the second derivative of this function. So then, of course, you can integrate, you get this factor, and you get just a factor b over 2, well, let me a over 2, because it's a second derivative. So you get b over h bar. So you see. So this is the value of this function at the minimum, and this is the contribution of the Gaussian integral when q are close to q naught. Okay? Example. And so why is this point is called a saddle? That's because, so this is a function, this is a potential, let's say, v of q. When you consider the function exponential of minus 1 over h bar v of q, this is a function which goes like that, since it's a Gaussian, with a minimum at q naught. So if you see that you have a mountain. You start from the plane here, you go up, you go to that saddle, and then you go down. So this is why it's called a saddle point. Okay. In fact, it's even better if it's called a saddle point, because now if you go into the complex plane for q, and consider what is the function which is the absolute value of exponential of minus 1 over h bar v of q, when q is complex. This is real along the real axis, but in the other direction, you see, it goes up, because when q becomes imaginary, you get an exponential of minus times minus, so it's an exponential growing. So if you think of this as a two-dimensional landscape, it has a plane here, a high mountain here, a high mountain here. If you draw the levels, you have something like that. Here, so imagine that you are looking at a map. See here, the h goes to infinity, so you go up. This is plus infinity, this is plus infinity. Here, the altitude goes to 0. You go down. So this is sea levels. You have two seas here. You have two very high mountains here. And to go from this plane to these planes, you have to go to this saddle, this path. Okay. Hence the name, saddle point. Okay. So now, what is the equation that satisfies? Well, to find Q minimum, you just have to use a calculus of variation that you start from Q. You assume that Q is Q minimum plus some delta Q, where delta Q is a small function, and you compute the variation of the Euclidean action with respect to some variation of Q at any points, let's say sigma, here between 0 and tau. Okay, and you want this to be 0. Okay, and if you want this to be 0, what you find, it's an easy calculation, for the action that I wrote before, for SE equal integral m over 2 q dot squared plus v of q. What, of course, you get for this equation is minus m, the second derivative of q, plus the v prime of q equals 0. Okay, so that's an equation at Euclidean time. Okay, so it looks very much like Newton's equation of motion, except that there is a plus instead of a minus. So now, play the same game at real time. Oh. Then the factor is imaginary. But if you think about the same example, so take this example when a is imaginary. So take integral from dq exponential, well, I over h bar a over 2q minus q dot squared plus b, you see, with the same potential here, but I have a factor I. And think about what is this function. So this function is a pure phase. So it has a real and imaginary part. And let me represent the real part of this. Okay? So the real part is a cosine of this object. So it's something that oscillates. But in fact, when q is very far away from q naught, it oscillates widely. And when q is very close to q naught, it oscillates very slowly because the variation of this are very small. Because the first derivative of this function vanishes at q naught. So in fact, the real part, if you think about the real part, and let me represent the real part as it's a function which oscillates widely here, but near q naught, it behaves like that. Okay? And the same for the imaginary part. So this was the real part, if you want. And if you consider the imaginary part, this is the sine of this object. So the sine, this vanishes when q equals q naught. So it's something that oscillates, the imaginary part oscillates like that, and it goes to 0 here, and then it starts to oscillate again. You see. So in all these domains, you have destructive interferences here. But here, you have something which is of order 1. Okay. So, the same argument shows you that what counts in such an integral is the behavior of this function near this point. But now, this is a point where the phase of this phase factor is stationary instead of the amplitude of this probability distribution that you want. So at that point, the q naught given by the same equation is called the stationary phase point. So now if we generalize that to that, you can check that at real time, what dominates is a classical trajectory, let's call it classical, q, such that the classical action is stationary under small variation q equal q classical plus delta q. In other words, the functional derivative of the classical action when you make a variation q of sigma is equal to 0. You see? And this gives just you the Euler-Lagrange equations, which in this case read minus m q dot squared minus v prime of q, the gradient, is equal to 0. So this is Newton's equation. So you see that in this case, in real time, when I perform a path integrals between initial and final configuration, you have a sum over all possible configuration. That's what I wrote here. You have a sum over a lot of different histories. But when h bar is close to 0, what comes important is the classical trajectory, which is a solution of an equation of motion, a classical equation of motion. And trajectories that are far away from the classical trajectory, well, undergoes destructive interference in the path integral. The phase cancel very much, except in a region which is, so there is a region here close to the classical trajectory where you get no interference. And here you have lots of interference. You can forget about what's happening here. Okay. And this point, so this trajectory is called the stationary phase trajectory. So this is called the stationary phase approximation. And of course, what you get is that in this case, this real-time propagator, K, is just, in first approximation, exponential of I over h bar S of the classical trajectory. So the dominant phase in the propagator is just the exponential of the classical trajectory, solution of the classical equation of motion when h bar goes to 0. Okay? So that's one of the nice aspects of path integral that was noticed by Feynman when he invented path integrals, which is that classical mechanics emerge from quantum mechanics. Because remember, the path integral was constructed out of a quantum Hamiltonian. So if you had your quantum Hamiltonian and didn't knew that you had obtained by applying, canonical quantization rule, but you are given a quantum Hamiltonian, you can deduce the classical equation of motion out of the quantum equation of motion, for instance, through the path integral formalism. Okay? So in this formalism, classical mechanics come out from quantum mechanics, which is the right way to think about classical mechanics. Classical mechanics is an emergent simplest dynamics coming out from the quantum world. Okay. What time is it? Okay, so yes?
Is there a way in which we can make it more precise that actually h bar is constant? It doesn't go to 0, but it's somehow fluctuations of the action that go to infinity?
You want to understand what's going on near the classical trajectory?
Yeah, so in classical mechanics, if I take a pen and I throw it to the board, it doesn't actually take on that many paths. And the reason is not that h bar is smaller for that, h bar is constant.
Yes.
The reason should be something like the variations of the action should be big.
No, I think I think that's precisely because h bar is very, very small compared to, throw a pen to this blackboard. So the pen has a mass, a few grams or tens of grams. And it has some velocity, let's say a few tens of meters per second. And compute the action for the trajectory.
Yeah, but the action...
And compare it to h bar, the unit of action in the quantum world. And you'll discover that it's much, much bigger, because basically the action is a number of, or the one in the CMS system, I don't know, and h bar is very small.
The action doesn't matter. I can rescale everything. And
no, you cannot rescale the action independently of h bar. What you have to compare, when you have a classical system, that's what I said, when you have a classical, when you have some process, some dynamical process, to know whether you can use a semi-classical approximation to compute what's happening, you have to compare, if it was classical, the action for this process to h bar. And if the action is of order of h bar, it's clear that you have to take into account the full quantum mechanics, solve Schrödinger equation. If the action for this process is much, much bigger than h bar, then you can use classical mechanics in most cases.
My point is that the magnitude of the action itself doesn't matter here. It's the variations that matter.
No, it's the action. Because you see, this is exponential of I over h bar s of q. So you have to compare this and this.
But that's just a prefactor that is everywhere. I could just bring that outside if I want.
Okay. I see what you mean.
I can bring it out of my entire
integral. I see what you mean. Okay. Yeah. Okay. I see. No, good point. I see what you mean. Well, you have to compare this also to the mass of the particle. Okay, I think I will answer that question. Is the last point I wanted to discuss, which is how you represent the position of the impulsion operator, the momentum operator. Okay. Because we are going to see precisely what is the width of this domain. Okay?
That width should be bigger for a classical object.
No, it will be smaller for a classical object than for a quantum object. Okay? And I'm going to show you in a simple case how you compute this width. And this width is related, of course, to the mass of the particles, because in some sense you understand that if you have quantum fluctuation, if the particle is very massive, the quantum fluctuation will be much smaller along the trajectory than the classical trajectory. Okay, so this is related to computing what is the momentum. Okay, so the momentum in classical mechanics, of course, it's called little p, is just m times q dot. This is classical. Okay, you believe me. Now, think about what is the momentum operator in a path integral. So again, I am at real time. I compute this path integral between q initial and q final. And if you want to think about what is p, you have to be more careful. You still have to remember that you discretize time. So I have a epsilon equal delta t, which is a time step. This was an intermediate approximation in constructing the full path integral. What's important is the continuum limit. And you sum over all trajectories with fixed boundary condition. And we have seen that if you are interested in representing the position operator, the position operator is represented by the position of the particles at a given time t. So the position q at time ti is associated to the time ti equal t divided by n, where n is the number of steps. Okay, so the time intervals. Now, it's quite clear that if you want a p which corresponds to the velocity, you have to associate p to, let us say, ti plus 1/2, which is associated to a time interval. So what I'm calling ti plus 1 here is just the interval between I and I plus 1. Okay? So here, what I call ti plus 1 is associated to the time interval ti and ti plus 1. Okay? So a natural definition for p in the path integral is to represent p as q at time ti plus 1 minus q at time ti divided by delta t, that's the velocity, times m. So let me assume that this is a way to represent P in, so P is associated to, so you see, P is associated to this, while the positions are associated to the position of the particle here and here. Okay. And you can check that if I want to compute a matrix element between a final step, a final and initial steps, I'm using the Heisenberg representation, and I want to compute P at a given time t. This is represented by this path integral between t initial and tf, where here I have t1, let us say, where t1 is here. This is t1, you see. So this is the way path integral are represented in the, well, position, momentum operator are represented in the path integral. This is given by path integral dq ei over h bar s of q, and what you have to insert is m over 2 q of ti plus 1 half minus q of ti divided by delta t. Okay? Good. So, momentum operator can be constructed in the path integral, but you have to be a bit more careful because you have to associate it to intervals, time intervals, before taking the continuum limit, the continuum time limit. You cannot do that after, because after that, you do not have time intervals. So you must define P before taking the limit delta t goes to 0. Okay? Good. So that seems okay. But
T1?
T, yeah, I call it T1 here. Well, you have to take the interval here where such that T1 is in between Ti plus 1 and Ti. Okay, and so when you vary the mesh, of course, the interval where T1 will be located will be different, and what you keep is T1. So for a given mesh, you look at the interval where T1 is located. This is T1. And then you take the limit, and that each time you pick up just the interval where T1 is, and you take the limit. Okay? That's what it means. And, well, this works for one P, this works for several P's, this works for combination of P's and Q's, etc. Okay, so P are easily defined in path integral. So this is a path integral receipt for momentum operators. Yes?
Path integral, why did you divide by 2?
Why?
Why did you divide by 2?
Why is it divided by 2? Because it's a mistake, because I made a typo. There is no reason for it to. Yes, thank you. Yeah, of course, it's M. Okay, thank you. Yes?
So what's it between the initial time and the final time?
Yes?
Here we are inserting, was it Q or P? There were some sort of observables. Should we think of them as really observables that we put in there somewhere in between and make a measurement? I mean, so does that not change the dynamics after the measurement?
I'm sorry, I'm not sure I understand completely. Okay. You're asking whether this corresponds to making a measurement of P?
I don't know without the
Oh, okay, this is just a matrix element of an operator. So it's a mathematical, it's a complex number, which is given by you take this initial state, you multiply it by this operator, an operator in the Hilbert space, and you take its product with this final state. So it's just a matrix element between those two initial and final state of this operator. This is an operator. There is no difference between what I did with Q operators, except that now I am considering the momentum operator.
Can you describe us maybe a situation where that would be realized in
Well, this doesn't correspond to measuring P, because measuring expectation value operator requires a projection operator, a projective measurement. So it requires computing probabilities and not probability amplitudes. So it requires taking two objects like that, for instance, and then taking their square. And each of the probability amplitude is represented by a path integral. So when you compute quantum probabilities in path integral, you need to introduce two path integrals, one for the amplitudes and one for the conjugate amplitudes.
So my question is, for example, if you wanted to measure momentum at time t1,
yes?
Does that affect the dynamics after t1?
Of course, it will affect the dynamics. Here, I am considering that the dynamics is completely free, and I compute a matrix element for this dynamics. The dynamics is of an isolated quantum particles between the initial time and the final time. So inserting a P doesn't correspond to measure P, because if I was measuring P, I would have a collapse of the wave function, or whatever you call it. You like to call it in quantum mechanics. And the dynamics is affected because of the Heisenberg uncertainty relation. So this does not correspond to measuring P.
So where could this kind of calculation be useful?
It's useful because for instance, in perturbative calculation, perturbation theory in quantum mechanics, these objects play a role. If you have not seen yet, I think in quantum mechanics course, you have seen mostly theory of quantum measurements, a lot of things. But if you are interested in atomic physics, physics of atoms, and you are going to see that, I think, in the condensed matter course, then this kind of matrix element plays a role. And they will play a role in quantum field theory too. So this is useful. Otherwise, we won't spend so much time in, well, it's not a real argument. But well, if one is interested in the subject, because they have to be calculated in order to do physics. It's not just because they have a nice mathematical object. They have nice mathematical properties, but it's not only that. Okay. Okay, so let me... Okay, so this is the definition for the momentum operator. So everything seems nice, except that something interesting happens if we want to measure what are the fluctuations of the momentum P at a given time. Okay? Because quantum fluctuations. Okay, so let me consider the simple case of a particle like that, and for simplicity, I'm going to consider a free particle. Free particle. So the Hamiltonian is just going to be P squared divided by 2m, and there is no external potential or constant external potential. The particle, so the solution of problems are just plane waves. That's just solving the Schrödinger equation for a particle in space, just its mass. Okay, so that's the simplest. Okay, so in this case, this kind of object is given by a path integral, where the action is just, so the action is just integral ds m over 2 q dot squared of s. Okay, it's just a kinetic energy. Okay, and if you discretize it, okay, if you want to see what are the properties of P, if you discretize it, the discretization of this is just obviously the sum from I equal, let's say, 0 to n minus 1, because we have time t0, t1, t2, up to t final. ds becomes delta t. Q dot squared becomes Q of ti plus 1 minus q of ti divided by delta t squared, and I have a factor m over 2. Okay, so this is a discretized action. So you see, and you recognize here that this is something like, this is the velocity, which is there. If I take m squared and I divide by m squared, what I get is that I get delta t over 2m p squared discretized at time t I plus 1/2 is my notation. So I get a sum from I equals 0 to n minus 1 of the objects that represent the momentum. Okay. So you see that now in this path integral, this kind of path integral becomes integral a product of a dq at times I, while I omit the normalization factor for the measure, and then I have an exponential of I over h bar times this sum. So I get a product over I from 0 to n minus 1 of exponential of I over h bar, okay, delta t over 2m times these quantities that represent p at time ti plus 1/2 squared. You see? So you may consider that the path integral, instead of thinking of it as a path integral over position, you can think that at the initial set, the position has a velocity q dot 1 or some momentum p1, then it has a momentum p2, then it has a momentum p3, p4. You see, so you can consider that for the free particles, the particles, you know, it has some classical momentum, and then the classical momentum gets heated. Get that, and this is a probability distribution for instantaneous momenta. Okay. So the phase associated to the momenta here is completely independent for the phase factor associated to those momenta. You just add momenta which are independent. So in some sense, this is a Markov process. You can view this as a Markov process in the momentum space. A Markov process, I mean that the momenta of the particle, the velocity of particle at that step has nothing to do, it's an independent random variable from what's happening previously. Okay. And the weight associated to this Markov process, well, this is not really a probability, it's just p squared, so it's like a Gaussian process, but with a factor which is delta t times m h bar. You see? So now if I'm uncertain what is the expectation value of p squared at a given time t, I'm not going to do the calculation exactly. It's not a complicated calculation. But since this is a probability, well, the imaginary, the phase distribution associated to PTI, if I compute the expectation value, so what is the average of the square of the velocity at a given time, this is just proportional to the inverse of this. Because if this was a probability distribution, the expectation, the variance of this would be the inverse of the factor here. So this has to be proportional to m h bar divided by delta t. Okay? Yes. M. Oh, no, there is a 1 over m here. No, that's okay. 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 So this is an important equation. Because first you see that the fluctuation of the momentum are proportional to h bar. So the smaller h bar, the smaller the fluctuation of p square r. So h bar measures indeed the amplitudes of the quantum fluctuation. That's fine. So this is a quantum fluctuation. Okay, first point. Second point, this is proportional to m. But p is m times the velocity. So it means that the fluctuation of the velocity are proportional to the inverse of the mass. Okay, so the fluctuation of the velocity squared are proportional to 1 over m, h bar over m. The larger the mass, the smaller the fluctuation of the velocity. And that's because the particle, even if it undergoes quantum fluctuation, if it's very massive, it has a big inertia, so it reacts more slowly to this quantum fluctuation. It's a picture. Okay, so that's okay, good. When the mass becomes large, the quantum fluctuation of the velocity are smaller. And this means that basically this width has to be proportional to 1 over the square root of the mass, because the velocity is the position squared. Okay. Good. So basically, what this argument says, I'm not going, is that the width here, the width is proportional to square root of h bar divided by the mass of the particle. So the bigger the mass, the more classical the trajectory is. Yes?
Why the width related to expectation value of these? Where
why?
Like why the width of your relevance trajectory?
You have a Markov process here for the velocity, and so it will correspond to what's called a random walk, a Brownian walk. So in fact, for this model, the probability distribution for path is related to the probability distribution of a Brownian walk or a Wiener process. And if you want to know how the position vary, you just have to integrate the velocity and compute. Okay? Well, I don't have time to discuss that in detail, but we can discuss that. I can show you how this is done. Okay, so we have some physical, this has nice physical. First, the fluctuation are proportional to h bar. The fluctuation of the velocity are proportional to the inverse of the mass. But you have this delta t, which means that in the continuum limit, this becomes infinite. Okay? So this means that this path, in fact, in the continuum limit, in the limit, when delta t goes to 0, the paths we have here, well, are related to Brownian motions, but not exactly Brownian motion because the distribution is a phase instead of particle, but it's Brownian motion like. So it's related to what is called a Wiener process in mathematics. Okay, and also this is a reason why Feynman path integral is often referred in the mathematical and mathematical physics literature as the Feynman-Katz integral, because it has been studied by the famous, I think he was Russian at that time, mathematician Katz. It's one of the old Katz. We studied this process. Okay. Okay, so And what's happening is that you see, if the velocity is, if p squared is over h squared, it means that the velocity is also proportional to 1 over delta t squared. So the fluctuation of the velocity are infinite. So it means that a typical path that's have to be taken into account in the path integral are paths that have the properties of a Wiener process or a diffusion process, which means that they are continuous but not differentiable. The derivative is infinite at every point, or almost every point, in the sense of measure theory. If you take a typical configuration, except on a set of points of measure 0, the velocity is infinite. Okay. So, and it is infinite in the sense that if you consider what is the average velocity between the point t and the point t plus delta t for this process, the fluctuation of the velocity diverge in this way, as 1 over delta t. I'm going to show you tomorrow, I think, a picture of random walk situ, of Wiener processes, if you have not seen them. Okay, so they are continuous, they are not differentiable, and I think in the math literature, they belong to a class of function which is called 1/2 Hölder functions, if you are interested in the mathematics. Okay? So this is I think the answer, you see. The functions that play the role in the path integral are functions that are continuous, that are localized around the classical trajectory. So they do not go too far away from the classical trajectory, but they are much more wild than for the classical trajectory, because the classical trajectory is, of course, a continuous function, but it is differentiable, and in general, it's of class C2 or C3, so it has a first derivative, a second derivative, etc. So the path, the histories in the path integral have no derivative. But nevertheless, the path integral makes sense. Okay? Okay. So I hope this consideration help you to understand what are the typical configuration here. These are Wiener processes that fluctuates around the classical trajectory, but whose velocity fluctuates much more in a much more singular way. Okay. And that's important for many aspects of many quantum features of the quantum particles comes out from the fact that the histories in the path integral have no derivatives. Okay. So I think I'm going to end up there the discussion about path integral. And I still have 20 minutes, so let me just start to generalize what we did for the scalar, the Klein-Gordon field, so the scalar field. So now from quantum mechanics to quantum field theory, relativistic physics. Okay. So what is first the classical scalar field? Okay. So I am in space-time. So I'm going to represent C by time and position. I'm taking the Minkowski matrix to minus t squared plus d x squared. So I am using the minus plus signature. And a classical scalar field means that you have your space, and at each point in space and time, to associate a field phi of x, which is a real variable. Okay, because it describes a field with no spin and no charge. If the field was charged, it would be a complex field because it has to carry a U1 charge. And if it was a spin, it would be a Dirac fermion or a vector if it had spin. So it's been no spin and no charge. Okay? That's just a Klein-Gordon field. That results for second quantization of bosons, which are massive. Okay, so now what is the action, the classical action? The classical action for, so I consider a field configuration phi. So phi means that I have an application. So phi means that I have a function from to each x I associate phi of x for x belonging to R D. And let me assume that I'm in D dimension. So in 1 plus D minus 1 dimensions. So this is time and this is space. Okay? So the action that describes the classical dynamics of the scalar field is just integral over T of a Lagrangian. And the Lagrangian is an integral of a Lagrangian density, d minus 1 of x. And the Lagrangian density is 1/2 of d phi over dt squared. This is the kinetic part associated to the field. And then a minus 1/2 the gradient, so the derivative with the space of phi squared. And then there is a term which contains the inertia of the particles, so which is minus m squared over 2 phi squared. Okay? So this is a Lagrangian density. This is the Lagrangian, and this is the action. Okay? And you have to keep in mind that this is the kinetic part, and this is the potential part. So we can write this as this plus this. This is the potential part. The analog in a classical system. This would be V, and this would be Q dot squared, m divided by 2. Okay. So this is a classical action. And of course, the classical equation of motion can be written as by applying an Euler-Lagrange equation. And Euler-Lagrange gives you equation gives that let me check that I made no mistake I've not written there here. I might do a mistake, so I get a minus. I'm going to have plus. Which means that I have a minus d over dt, d squared over dt squared, plus d squared, well, d over dx squared, minus m squared phi to 0. Up to possibly a sum. Okay, so this is a Klein-Gordon equation. Okay. Good. So, since I am going to reproduce So now I'm going to just use what we did in quantum mechanics to consider this field as a quantum mechanical system, but a quantum mechanical system with an infinite number of degrees of freedom. That's it. So you see, because you have, here I have my space-time, it has time, and it has x, the x variable. Let's assume that I have in 1 + 1 dimension. That's it. So if you want to construct a path integral to construct this term, we have seen that we have to discretize. We discretize time. With a factor delta t. But still, at each intermediate time, we have phi of x and t. So the variable is phi of x, which is phi of t and x, position space. So if we discretize time, at each discretized time, we still have an infinite number of variables, which is the value of the field at the point x. Because the classical configuration is a field configuration along this time slice. So it's quite natural to make things to discretize space 2. So instead of considering a continuum space, I consider a space which becomes a lattice. Okay, and so here I have a mesh which is delta t, and I consider a space mesh which is delta x. Okay, take a lattice of the form zd minus 1. Okay, so you see that space-time becomes a lattice, a d-dimensional lattice. Okay, and it's quite natural to choose that delta t equal delta x equal what I'm going to call epsilon. Because, of course, the classical scalar field is invariant under Lorentz transformation, so which mixes space and time. So in this discretization, it's a good idea to treat space and time on the same footing. It's optional. You can do without it, but it simplifies the calculation. Okay? Of course, so space-time, Minkowski space-time, M1 d minus 1, becomes a lattice z to the power d, which breaks Poincaré invariance. For the same reason that when we discretize time in quantum mechanics, we break time translation. Time translation becomes discrete. Here, time translation becomes discrete, space translation becomes discrete, and Lorentz boost disappear completely. We have to check at the end of the procedures whether we get that. So we have to be careful. Okay, so I'm going to try to define what is a path integral for this object by just applying the recipe we had. Yes?
There's no discrete rotation or anything invariance left?
I don't think so, except time and time inversion, time reversal, and parity.
That's not a Lorentz, like that's not a
No. No. The reason is quite simple. The reason is that when you perform a Lorentz boost of that, what you are going to do is you are going to get a lattice like that. Okay? Which is not at the same time if you make a boost. Okay? Is it clear? I think there is a way. I think Feynman devised another discretization, which is discretization in light cone variable. Because if you discretize, imagine you rotate your lattice by, in 2 dimensions, I rotate my lattice by pi over 4. Then this axis becomes null directions, light variables. And then they are preserved under boosts. There is some transformation, but the transformation preserves part of it. But I'm not going to do that. Okay? And it works, I think, in 2 dimensions, especially, only. Well, this is going to be done in any dimension. Okay, so I want to discretize time, to discretize space, and to construct a path integral. And I'm going to do that both for the theory at real time and the theory at Euclidean time. So, but let's do that for Euclidean time here. Okay, so first, the Euclidean action at, the action at real time, I can rewrite this, of course, as integral d dx. So capital X is a space-time vector. And I get minus 1/2 d mu phi minus m squared over 2 pi squared. Okay, this is a covariant action for phi. And there is a minus because I'm using the East Coast metric. It would be a plus if you use the West Coast metric signature that you use. Okay, good. So now this is real time. Think a little bit about what's happening if you want to define the theory at real Euclidean time. Now we have a theory where we have time and space. So let me take this plane and rotate it like that, so that it's horizontal. Okay, so I have a plane that represents time discretely both. So this is time, real time, and this is x, this is space. Okay, so space goes like that, time goes like that. Okay? Now, if I want to perform a Wick rotation, I have to perform a rotation in the complex plane of time by an angle minus pi over 2. So my blackboard is going to be the complex time plane. And space goes in this direction, if you want. Space is orthogonal. So performing a Wick rotation means changing the time, but do not changing space. Space is real, it remains real. So I perform, so this is a plane, let's say. So you see, this is a plane. You have this plane that is Minkowski space-time. This is Minkowski. M11 if I am in 2 dimensions. Rotating time means I perform a Wick rotation. So now it is this plane, you see. Well, this is Euclidean time. Tau. Remember? So when tau is real positive, t is imaginary with a negative imaginary time. So tau is IT. Okay? So this is Minkowski space, and when I perform a Wick rotation, like that for the axis, I get a plane with x and tau. So Minkowski 1, 1, if you want, or 1, d minus 1, is a t x plane. Okay? But the tau x plane is Euclidean space-time. So it's just the plane RD, simply because the line element d is squared in this sphere is d tau squared plus dx squared. Okay, so this is Minkowski and this is RD. Okay, so here you think about the Minkowski, performing a rotation. You take your Minkowski spacetime and you rotate it in the time plane, not in the x plane. Okay. So now, if we perform this transformation, what is the corresponding Euclidean action? Well, you can play the same game that I did because, so I make a Wick rotation, so I change t in tau. So this is dt. I do not change x, d minus 1 of x. I'm sorry, this is now an integral over tau. This is an integral over x that doesn't change. The kinetic term doesn't change, d phi over dt squared. And the potential terms change sign. So this is plus 1/2 d phi over dx squared plus m squared over 2 phi squared. Okay. So this is a classical action in Minkowski spacetime, and this is the corresponding Euclidean classical action for a field configuration in Euclidean spacetime. Okay? And you see that the Euclidean action takes the form integral d4x Euclidean, because if I assume that x Euclidean is a d-dimensional vector tx, while x Minkowski is tx, I integrate over x, and then I get here 1/2 of d mu phi, but this is with reference to the Euclidean metric, plus m squared over 2 phi squared. Okay. So this is a real-time action, and this is Euclidean time action. Okay? And now we want to define a path integral for this. What is a path integral? For this quantum field. Okay? Well, by analogy with what we did for quantum mechanics, we expect this to be just an integral over all field configuration that I'm going to define tomorrow, times a phase which is exponential of I over h bar times S of phi. Okay, so we expect that quantizing the theory by path integral methods amounts to integrate over field configuration. So I integrate over all fields over MD. So the path integrals becomes what is called a functional integral. Okay. And the quantum phase is exponential, is proportional to the action of the corresponding configuration. So of course, this is very formal. And what I'm going to do tomorrow is to look at what is a proper discretized form for this. And then I'm going to discuss how you take and whether there is a continuum space-time limit, because to make things sensible, you discretize both time and space, and therefore, when you want to recover continuous Minkowski space-time, you have to take both delta t and delta x to 0. And we'll see that there are some interesting differences between quantum field theory and the quantum mechanical system. Okay. But let's end this lecture here. Thank you.